Good morning, students. In this lecture, we will discuss about binary counters, Boolean operators, and shifter circuit of your fourth unit. Fourth unit of VLSI system design. Now, these notes is according to your reference book Neil Weste. So, before starting this topic, first we have to know that what is the mean of counter, why we use this counter circuit. Okay. So counter is nothing but a sequential circuit. Now what is the mean of sequential circuit? Now what is the mean of sequential circuit? Now what is the mean of sequential circuit? Sequential circuit is that in which the output is not only depend upon the present input, but it also depends on the past output. Okay. Now why we use these counter circuit? Counter circuit is mainly used to count the clock pulse that is provided in the circuitry. Now the question arises that what is clock pulse? So clock pulse is nothing but a time interval that is provided to any combinational or sequential circuits. Okay, so we already know that we already studied this topic in our digital electronics that for making counter we need flip-flop, because flip-flop is a memory storage element. It stores 1 bit of memory. Okay, now how we can make this flip-flops? Any flip-flop can be made by combining various logic gates. And how can we make these logic gates? These logic gates are nothing but a combination of transistor. So it means that transistor is the smallest element through which we can generate any type of counter. Or in broad way we can say, when we combine several transistor, when we attach several flip-flops into series, then we will get the counter circuitry. Okay, so we know that there are the various types of flip-flop, such as SR, JK, D, and T. Okay, we already know that these are the types of counter, these are the types of flip-flops, these are the types of flip-flop. It means that it means that it means that for making any devices we can use these type of flip-flop. For making any memory storage element, for making any resistors, we can use these type of flip-flops. But when we design counters, so for designing of counter circuit, we always use T flip-flop. We always use T flip-flop because T flip-flop consists a different feature that doesn't exist in SR flip-flop, JK flip-flop, and D flip-flop. What is that feature? That feature is toggle. That feature is toggle. It means that when clock pulse is provided into T flip-flop, and at that time if the present input is 0, so when we provide clock pulse, then the output will be toggle, and if it is 0, then now it moves towards the 1, and if the output is in one condition, so after providing the clock pulse it will be 0. Okay, so this flipping property is known as toggle. This flipping property is known as toggle feature. Okay, so this feature only exists in D flip-flop, and for making any counter this feature is necessary. So that for making any counter we always use T flip-flop. Okay, so there are the two types of counter. One is known as asynchronous counter. Asynchronous counter is also known as ripple counter. Asynchronous counter is also known as ripple counter. Okay, in this type of counter, when several T flip-flops are connected into series, then output of one flip-flop is act as a clock pulse for the next flip-flop. It means that next flip-flop not works till the first flip-flop provided output as a clock pulse. Because of this feature, this type of flip-flop having the lowest speed. Okay. Now the second type of counter is synchronous counter. Now the second type of counter is synchronous counter. As name suggests, synchronous counter is that in which all clock pulses are in synchronized form. Now what is the mean of synchronized form? Synchronized form means all flip-flops getting the clock pulse in the same time interval. So if all flip-flops getting the clock pulse in same time interval, then definitely it will provide the output in the same time interval. So that's why this synchronous counter is fastest among the all different type of counters because of its characteristics. Okay, so we can make several type of we can also divide counters into several types, such as up counter, such as down counter, such as binary counter, etc, etc. Okay, if we are dividing counter on the basis of its counting sequence, then we can divide counter into two parts. One is up counter and another one is down counter. If the counter if the counter counts the clock pulse in the form of ascending order, then it is known as up counter. And if the counter counts the clock pulse in the form of descending order, then it will known as down counter. And also, if we want to divide the counter on the basis of its if we want to divide the counter on the basis of its clock pulse, then we can also divide counter then we can also divide counter into decade counter, octave counter, etc. These name are on the basis of its counting number. Okay, here one diagram for asynchronous up counter is shown here. Here one diagram of asynchronous up counter is shown here. This type of counter is made with by using T flip-flop. Okay, suppose I don't have T flip-flop, I only have JK flip-flop or SR flip-flop. So the question arises that is it possible to implement the counter by using these other flip-flop? So the answer is yes, it is possible. But in that time, first we need to convert that type of flip-flop into T flip-flop, after which we can implement the counting sequence, we can implement the counter. Okay, now here I am showing you the diagram of 3-bit up counter. Okay, so each flip-flop, we know that each flip-flop is known as memory element, and each flip-flop having a capability that it only stores the 1 bit of memory. So because there are the 3 flip-flops and that are connected into series, so we can say that the combination of these flip-flop stores the 3 bit of memory. That's why this type of counters is known as 3-bit counter. Okay, the counter who is getting the clock pulse, who is getting the clock pulse, the flip-flop who is getting the clock pulse in very first time is always provide the LSB bit. That's why I am writing here Q0. And the output of first is provided as an input of second. Output of first is provided as an input of second. That's why this type of counter is known as asynchronous, because the output of first is act as an input of second, the output of second is act as a clock pulse for the third. That's why this is known as asynchronous. And because there are the 3 flip-flops are connected into series, that's why it is known as 3-bit asynchronous counter. Now why it is known as up counter? Now the question arises that why it is known as up counter. Okay, now the answer is that when we provide clock pulse in very first time, at that time the output of these flip-flops are 0 0 0. But when we provide clock pulse, so this 0 0 0 will change and it will be 0 0 1. After second clock pulse, the output of these clock pulse is 0 1 0, and the second clock pulse, after the third clock pulse, it will be 0 1 1. Okay, 0 1 1. In very first time, the output is 0 0 0. I am writing here, this one is Q0, this one is Q1, and this one is Q2. So when we start our counter, at that time its output stage is 0 0 0. But when we provide the clock pulse, at that time this 0 0 0 will be changed and now it will be 0 0 1. It means that after providing first clock pulse, this will be 1 and these two inputs will be 0 0. Okay, now after providing the second clock pulse, now the output will be 0 1 0. It means that Q0 will be 0 and Q1 will be 1 and this will be 0. Okay, after providing the next clock pulse, after providing the third clock pulse, the output will be, after providing the third clock pulse, the output will be 0 1 1. Okay, it means that when we provide third clock pulse, so it output will be 0 1 1. When we provide second clock pulse, then the output will be 0 1 0. When we provide first clock pulse, then the output will be 0 0. When we haven't provided any clock pulse, at the time when the counter is in reset condition, at that time the output will be 0 0 0. It means that the output of these flip-flop represent the binary form of the clock pulse, that is provided into the circuit. That's why it is known as counter circuitry, because it counts the clock pulse. Okay, now I think this topic is clear to all of you. Now we are moving towards the synchronous. Now we are moving towards the asynchronous down counter. Now we are moving towards the asynchronous down counter. Now, as name suggests, that asynchronous down counter is that in which the counting sequence is ascending to descending order. It means that when we provide the first clock pulse, at that time the counter provides the maximum counting stage. It means that when we provide the first clock pulse, at that time the counting sequence will be 1 1 1, and when we provide the second clock pulse, at that time the counting sequence will be 1 1 0. It means that the counting sequence decreases one by one, and because of this down sequence, this type of counter is known as asynchronous. This type of counter is known as down counter, and because the output of one is act as a clock pulse for second, the output of second is act as a clock pulse for third, and because of this property, this type of counter is known as asynchronous counter. This type of counter is known as asynchronous counter. I think this topic is clear to all of you. Now the second type of counter is synchronous counter. Synchronous counter is that in which all flip-flops getting the clock pulse in the same time interval. Here you can say, here you can see this feature of synchronous counter. Here you can see all flip-flops getting the clock pulse, simultaneously. That's why all flip-flops provided the output simultaneously. So when all flip-flops work simultaneously, so because of this feature, its speed is fast as compared to asynchronous counter. Okay, I think this topic is clear to all of you. This diagram is the 4-bit synchronous counter. Why 4-bit? Because here 4 flip-flops are connected to form a counter. That's why it is known as 4-bit synchronous counter. Same as if the counting sequence is from 0 0 0 to highest level, at that time this type of counter is known as up counter. Here you can say the starting stage is 0 0 0 0, and after providing the each clock pulse it will be move one bit ahead. So zero, after providing the zero, after providing the 0000 output, it will be 0001 output, and for and in next clock pulse it will be 0010, and it moves till you find the highest stage of counting. So because of this ascending order of counting, this type of counter is known as asynchronous up counter. Asynchronous up counter. Okay, asynchronous up counter. If there is no gate connected with this type of syncage, if there is no gate connected with this type of flip-flop, so any counter counts 2 raised to power n stages. It means that if 4 flip-flops are connected to form a counter, then it counts total 2 raised to power n minus 1. That means it counts total 15 clock pulse. Okay, so by using this type of logic gate, we can minimize the counting sequence, according to our requirement. Okay, so this one is all about the counterpart. This one is all about the counterpart, and this one is the CMOS structure. This one is the CMOS structure for designing of synchronous counter using a adder and D flip flops. Okay, here you can say one diagram of counter is shown here. It is made by using D flip flop, and we already told you that any counter can be implemented by using any type of flip flop, but before conversion it is required that first is to be converted into T flip-flop. So here first we convert the D flip-flop into T flip-flop. After converting that by using this up down signals and by using clear clock pulse, we can provide it input sequence, and it will gives us output, and this output is act as a up counter, act as a counter sequence. Okay, so this is all about the counterpart of your VLSI system design. Okay, here this down sequence, here this up down sequence, here this up down sequence is nothing but a signal. The flip-flop works on down sequence of counting, or it moves towards the up sequence of counting, and here this clear pulse is applied to reset the clock pulse, to reset the flip-flop. Okay, when this clear pulse is 0, so the clear bar will be 1, and when this clear bar will be 0, and when we provide this clear bar equal to 0, so it gets the signal of clearing the flip flop, and at that time the whole output of the flip flop will be 000. Okay, so this one is the counterpart of your VLSI system design. Here, according in your reference book, the theoretical part of your asynchronous counter is represented here. It is shown that it is also known as ripple carry, it is also known as ripple carry counter, or it is also known as binary counter, or it is also known as asynchronous counter. In this type of counter is made with by using T type of flip-flop. Same in this type of counter, the output of one flip-flop is provided as an input for the second flip-flop, provided as a clock pulse for the second flip-flop. Okay, that's why the speed is less in this type of asynchronous flip-flop. Now to speed up the process, if all flip-flop getting the clock pulse in the same time interval, so its speed will be higher, and this feature is exist in synchronous counter. This feature is exist in synchronous counter. That's why we can say the speed of synchronous counter is much higher. The speed of synchronous counter is much higher compared to asynchronous counter. Okay, the diagram in your Neil West book, the diagram for your asynchronous counter is shown here. The diagram for your asynchronous counter is shown here. Here you can say the output of one is provided as an input of the second flip-flop. That's why this type of counter is known as asynchronous counter. And because the inverting end of the because of the inverting end of the counter provides the output to the next flip-flop, that's why it is up counter. It is up counter. And if the non-inverting end of the flip-flop will provide the output of the next provide the clock pulse to the next flip-flop, then at that time it will act as a down counter. Okay, so this one is all about the counterpart of your VLSI system design. Now the next one is Boolean operations. Boolean operations. Okay, Boolean operations can be achieved by using any type of smallest element that present. Okay, in various circuitry, in various digital circuitry, the multiplexer is the smallest element. So by using multiplexer, the designer tried to design any type of Boolean operators, Boolean operations. Okay, here it is mentioned that the circuit, one circuit is present here, and it is made by using the multiplexer only. Okay, this one is the representation of synchronous up down counter. This one is the representation of synchronous up down counter. In synchronous up down counter, all flips of getting the clock pulse in the same time interval. Okay, and this up down is the signal that provide to the flip flop, and according to it, it moves toward the, it counts the up sequence or down sequence. Okay, this one is all about the ALU part of the ALU part of the circuit. This one is all about the ALU part of the syllabus. Okay, here one multiplexer, here the three multiplexers are present, and by using these multiplexers, some Boolean logic is trying to implement. Okay, here you can see in the second level of multiplexer, two multiplexer are present, and in these multiplexer selection lines are common. So when we provide any input, so it will reach in the both multiplexer, and output of it is provided to the multiplexer that exists in for level first. And according to this B signal, according to this B selection line, it will provide the binary logic. Okay, so this one is all about the Boolean operations that we can implement by using any smallest element, by using any type of multiplexer. Here here one here one circuit is also present. Here one circuit is also present. According to this circuit, we can say, we can say, here some selection lines are present. Here some selection line are present, such as S0, S0, S1, S2, and S3. And this selection line selects which input is provided in the circuitry, and which input is provided in the circuitry, and which will be in the rest condition at that time. So if B is the Boolean operation and A is the arithmetic operation, if B is the Boolean operation and A is the arithmetic operation, so by using this type of selection line, we can adjust that which type operation is performed in the circuitry. Okay, so accordingly we will select, and accordingly we will select the value of selection lines, and we will get the output. Same as this one is also a arithmetic logic circuit. This one is also a arithmetic logic circuit. This one is also a arithmetic logic circuit. Arithmetic logic circuit. Here one buffer is present. Here one bubbled buffer is present, and output of this bubbled buffer is provided to the NAND gate. And now here transmission gate is present. Here one transmission gate logic is present, and the output of this transmission gate is provided to the NMOS logic. Here this NMOS circuitry, this upper portion, this PMOS, is act as a load, and this below NMOS it is and this below NMOS connection is implemented according to the Boolean operation that we need to find in the output. Okay, some one more arithmetic logic circuit is present here, in which you can see one NOR gate is present, two NOR gate is present here, two NOR gate is present here, and output of it is provided to the multiplexer circuitry, and the multiplexer select these input according to the selection line. When the value of selection line is 0, at that time it will select the input that is provided in the port number 0, and the input of this port number 0 is transmitted to the output part. Okay, so this one is all about so this one is all about the arithmetic part, uh, boolean operations part of your boolean operation part of your VLSI system design. VLSI system design. Okay, now the last one is shifter. Now the last one is shifter circuitry. Now the last one is shifter circuitry. Where the shifter circuitry is present, where the shifter circuitry is present here, where the shifter circuitry is present here. Okay, the shifter circuitry is responsible to shift the data bit. Shifter circuit is responsible to shift the data bit. And if we want to shift the data with some boolean operation, with some logical operations, so it is known as logical shifting or arithmetic shifting. And if we want to shift the data, only shift the data, at that time it is known as simple rotation operation. Okay, so there are the two or three types of shifting. One is known as arithmetic shifting, logical shifting, or simple rotation. Okay, this type of shifting can be achieved by using 4x4 barrel shifter. 4x4 barrel shifter. Now what is the use of barrel shifter? Barrel shifter is nothing but a circuitry. Barrel shifter is nothing but a chart. Barrel shifter is nothing but a combination of various gates, in which by using this type of barrel shifter we can shift the data according to our requirement. According to our requirement. In 8.46 barrel shifter is represented. Here here the diagram of barrel shifter is present, in which you can see here various transmission gates are present. Here various transmission gates are present, in which these transmission gates are controlled by using the gate pulse. These transmission gates are controlled by using gate pulse, and when these transmission gate getting the clock pulse, when this transmission gate getting the signals, getting the input, so according to the selection line, it will provide it to the output circuit. It will shift the data. It will shift the data. These literals is responsible to provide the input in the barrel shifter. Okay, these literals that is connected here is responsible to provide the input in the transmission gate. And these shifted 3, shift 2, shift 1, and shift 0 is responsible to shift the data. It means that suppose I need to shift our data. Suppose I need to shift our data in one bit. Okay, so at that time this shift one pulse will be high. At that time this shift one pulse will be high, and rest of others are 0. So accordingly, these inputs that is provided from these literals are shifted one bit left. Okay, so this one is the diagram. So this one is the diagram, and this one is the cell layout of the barrel shifter circuit. Okay, you can understand this topic. You can understand this topic by using this structure. Here you can say these are the here you can say these are the here you can say these are the these cells are the gates. These cells are the gates. These cells are the gates in which inputs are provided, in which inputs are provided, and according to the selection input, according to this selection line, it decides the whether it is provided to one bit shift, or it is provided to the it is gain one bit shifting, or it is gain two bit shifting. Okay, so if the data is of, 4 bit, so n minus 1, that means 3 bit shifting is possible, because after 4 bit shifting it gained the same stage, it gained the same stage, that it gained the same starting stage, it, it gained the same starting stage. So this diagram, this diagram is shown the 4 bit barrel shifter circuit, and this one is also a logarithmic barrel shifter circuit. You can understand barrel shifter by using this simple gate logic, by using simple gate structure. Here you can say, here you can say this one is the gate terminal, this one is the gate terminal of, each gate, this one is the gate terminal of each MOSFET. Okay, so when the input of this gate terminal is 1, when the input of this gate terminal is 1, at that time, this input it is shifted, it means that, suppose I don't want to shift my data, it means I want shift 0, at that time I will provide the input of shift 0 terminal as 1. We will provide input of this shift 0 terminal as 1, and we will provide the shift 1 and shift 2 input as 0. So when the input of shift 1 and shift 2 is 0, so it don't works, only these three MOSFET are in working condition. So if this MOSFET is in working condition, so it provide this input 1 into output 1, this provide this input n minus 1 as output n minus 1, and this provide this input n minus I minus 2 as input out minus 2. When I need to shift my data into 1 bit, when I want to shift my data into 1 bit, so at that time I only provide the shift 1 operator as 1, and I will provide the value of shift 0 as well as the shift 2. I will provide the value of shift 0 and shift 2 as 0. So when we provide the value of shift 2 and shift 0 as 0, so at that time these three MOSFET and this one won't works, only these two gates are in working condition. So if these two gates are only in the working condition, so what happened? So what happened? So what happened? This input one. So what happened? This input 1, this input I minus 1 is transmitted in output I. Same as this input I minus 2, this input I minus 2 is provided in output I minus 1. It means that it shifted in 1 bit. Okay, so according to the requirement of the designer, according to the requirement of the circuitry, we can shift the data by using this barrel shifter circuit. So this one is all about your shifted part in your VLSI system design. I hope you all understand this topic very well. Okay, thank you so much.